So we're continuing Chapter 11, Part 2. This is where we left off. Reactions with HCl. Chloride is a weaker nucleophile than bromide because it's small and less polarizable. Addition of zinc chloride, which bonds strongly with the oxygen of the OH, promotes the reaction. It's also known as a Lucas test when you have zinc chloride in concentrated HCl. In general, primary alcohols for Lucas tests react slowly or not at all. Secondary will react 1 to 5 minutes, and tertiary reacts really well, less than a minute. So how does the Lucas reagent work? Well, if you have an alcohol, which I'll draw out briefly. So in this alcohol, you have your electrons. First thing that'll happen is that it'll coordinate with the zinc chloride. So here's zinc chloride, so electrons will go to the zinc chloride, in which you get this down and below. So now there's a separation of charges with a positive charge in zinc, and now from the other side, the chlorine from HCl will react, kick off, and generate the two species. And here is the intermediate. Again, this is an SN2 reaction, and so your nucleophile attacking and your leaving group leaping is happening at the same time. Primary alcohols react with Lucas reagent by an SN2 mechanism. This reaction is very slow. The reaction can take from several minutes to several days. Oh, sorry. So here is a more detailed reaction in terms of the Lucas reagent, but this time when under SN1 conditions. So secondary and tertiary alcohols will react via SN1. In that case, you have, again, the electrons forming that complex, but instead of nucleophilic attack from the chloride happening as the zinc complex falls off, you're going to have the formation of a carbocation. Once the carbocations form, chloride will come, quench that positive charge, forming the product and the byproduct. There are limitations of HX reactions, poor yields of alkyl chlorides from primary and secondary alcohols. Elimination competes with substitution, as you all know. Carbocation intermediates may undergo rearrangement, and there's a limited ability to make alkyl halides. So let's do a problem. When 3-methyl 2-butanol is treated with concentrated HBr, the major product is 2-bromo 2-methylbutane. Propose a mechanism for the formation of this product. So butanol, 2-bromo 2-methylbutane. So the first thing, right, we've seen this reaction before. Your alcohol gets protonated. Once it gets protonated, right, this is now a secondary alcohol. Once it gets protonated, it's going to leave, forming this secondary carbocation. After it forms that secondary cation, you're going to have a hydride shift, forming the tertiary carbocation, which is more stable. Bromine will quench that, and here's your observed product. Alcohols can also react with phosphorus halides. You get good yields with primary and secondary alcohols. PCl3 is used in terms for alkyl chlorides, but SOCl2 is better. PBr3 for alkyl bromides. P plus I2 for alkyl iodides, as PI3 is not stable. So here are examples of PBr3, P, and I2 in reacting with alcohols. So here's primary alcohol. In PBr3, essentially you substitute OH with the bromine. P and I2, primary alcohol, substitute OH with iodine. PBr3, OH and PBr, and Br. Now, in terms of mechanism, here's the mechanism of PBr3. The first thing that happens is you have your alcohol, right? That's your source of electrons, nucleophile. It's going to react with the PBr3 to the phosphorus center, kicking off the bromine and forming this complex. Now, once this complex is formed, that bromine that was kicked out comes and now attacks via SN2. That's really critical. Now, kicking off this whole thing, which is a good leaving group, and brominating your carbon here. So most important thing is that the oxygen attaches the phosphorus, displacing one of the halides, and that halide then attacks from the backside. Instead of using PCl3, SOCl2 or thionyl chloride is used. Alcohols in the presence of thionyl chloride and heat will then substitute the hydroxide group with a chlorine, and then your byproducts SO2 and HCl. In terms of mechanism, here's the mechanism. Here's thionyl chloride, your oxygen, again, is the source of your electrons. It will attack the sulfur and kick off the electrons to the oxygen. Once that happens, the oxygen electrons will come back down, kick off this chlorine. Now this chlorine is ready to react. This time, instead of, as in the PBr mechanism, reacting with the carbon, it'll pluck off that hydrogen, neutralizing the charge, now generating this chlorosulfide ester. This chlorosulfide ester will then remove itself, right, from the carbon, and then, interestingly, electrons from that oxygen will come down, and that chlorine will then attack the carbon of that carbocation, forming the two byproducts. An important thing to note is that thionyl chloride reacts with alcohols by various mechanisms and depends on substrate, solvent, as well as the temperature. You want to be cautious in predicting the structure and stereochemistry of the product unless you know the actual mechanism. Dehydration reactions, you've seen this before, right? H2SO4 in the presence of an alcohol will allow for elimination via E1. So concentrated H2SO4 produces alkenes. Carbocation intermediates are formed for secondary and tertiary alcohol, forms that Zaitsev product. Bimolecular dehydration will produce ethers at low temperature, right? 140 degrees below that favors ether formation, but at high temperatures, 180 and above, forms alkene formation. So let's do the dehydration of alcohol. Again, we've seen this reaction before, H2SO4, and you can draw that out. I'm not going to draw out H2SO4. You should know how to do that, especially in your mechanisms on exams. We'll protonate, get the protonated water. This will then kick off. And then either water will, now that you have the carbocation, either water will come in, pluck off that hydrogen, forming the double bond, or HSO4 minus can do the same exact thing. So you can have that actually react and kick off that proton, or pluck off that proton to form the alkene. In this case, rearrangements are definitely possible. And then the rates of reactions follow the same rate of ease of formation of carbocations, that is, tertiary is favored over secondary over primary. Primary alcohols rearrange, so this is not a good reaction for converting primary alcohols into alkenes. Mechanism of dehydration in terms of E1 in just a little bit more detail. Again, electrons from your oxygen will pluck off that proton from H2SO4, right? generating the protonated water. This will leave as a good leaving group, forming the carbocation, and then either water or HSO4 will come in and pluck off this hydrogen, putting the electrons down, forming the alkene. The energy diagrams, as we've seen before, here's energy as a function of reaction coordinate. You're starting off with your alcohol. When you protonate via H2SO4, it's slightly lower in energy. Here's your first transition state. Then this comes off. There's your second transition state. This formation of the carbocation is your rate limiting step. And then from the carbocation to the alkene, so while this is higher in energy, the alkene formation is actually lower in energy than all of them, and that has also a transition state. So predict the products of sulfuric acid catalyzed dehydration of methyl cyclohexanol. So here's methyl cyclohexanol. This is just showing proton, but when you're doing your mechanisms, I'd like you to show H2SO4. Sorry. As such, sorry, you're going to have to bear with my handwriting here. So instead of just showing as a proton, you're going to use the electrons plucking this off, and then the electrons going to the oxygen, forming the HSO4 minus. Then this will be protonated, this will leave, and now you form the carbocation. So it's the hint or the clue here is that it's saying predict the product. So you're going to have to predict all the possible products of this dehydration reaction. And so you have on this methyl group as well as in this methylene group possible hydrogens. So water can either pluck off one of these hydrogens, the HB hydrogens, and then form the double bond, or one of the two HA hydrogens and form the double bond. So here's forming HA, loss of HA, which will form the major product. It's tri-substituted, forming the Zaitsev product. Here's HB loss, forming a minor product, which is a disubstituted product. So vicinal diols can undergo following reactions: the pinnacle rearrangement, and the periodic acid cleavage. So in terms of pinnacle reagents, same thing. You're reacting this with H2SO4 and increasing the heat. So this will be an E1 elimination. However, it'll rearrange to form the ketone. So let's do the mechanism. Again, I would like to make sure instead of using just proton, H2SO4, showing that all out. Since I've already drawn it in the previous slide, I won't draw it for you again. But essentially, electrons from one of the oxygens of the diol will be protonated. After protonation, this will kick off, forming the carbocation. Once the carbocation forms, you have a methyl shift. This methyl group will move over, right over here, forming carbocation where the alcohol is. And it forms essentially a resonance stable carbocation, right? So there's resonance occurring here. So then electrons will come down. Now the positive charge resides on the oxygen. Now once you form this resonance stabilized carbocation, you're going to have water or HSO4 come pluck off that hydrogen and put the electrons to the charge, forming the pinoculone, and then protonated water. Periodic acid, cleavage of glycols. Here's your alkene. To form glycols, you can just use osmium tetroxide and peroxide, or cold dilute KMnO4, potassium permanganate. This will generate the glycol synaddition, as we've learned in the previous chapters. Then in the presence of periodic acid, HiO4, I'm going to cleave this essentially and form ketones and aldehydes. So it's kind of like just starting over here and going to here. You can use ozone, right, in DMS. But instead of that, you could do a two-step reaction in which you form the glycol here and then cleave with peridate. So here's the mechanism of peridate cleavage. I'm going to draw this out for you. Here's your alkene reacting with osmium tetroxide to form the cis glycol, and now your reaction mechanism starts with your electrons from your glycol, reacting, kicking off electrons to the oxygen. This will go down here. I'm going to draw it down there, so I'm going to move this up. Now you're going to have oops, sorry about that. You're going to have your product, which is not there yet, where one of the oxygens from the glycol has now reacted with the iodine. So this is positively charged. You still have your OH. I'm not going to show the substituents off of the ring so for clarity's sake, because I don't have much room and my handwriting's a bit awful here. So now you have this. You're going to have, I guess, these electrons pluck off that proton, neutralize the charge, and now you have your other electrons from this oxygen come here. Actually can kick this off because this can pluck off one of those protons and neutralize it. So this will generate O, iodine, double bond O here, double bond O here, and then your OH. So here is, and now I can draw in your substituents. Here's your methyl group, here's your hydrogen, here's your hydrogen, here's your methyl group. So this is essentially this, and this is how it's drawn much better than I could ever draw it using at least this, my finger here. Once you generate the cyclic peridate intermediate, now you just have cyclization occurring in which electrons from here go over here, from the single bond go to break, forming double bond oxygen, electrons go to the iodide, and electrons now go to there, forming this ketoaldehyde. So it really is, the step that you need to know is how it reacts with peridate. One of the oxygen gets on, the other one gets on to form the cyclic peridate intermediate, and then forming the ketoaldehyde. Important thing to note, periodic acid cleaves a diol to give the same products of ozonolysis, which I've talked about. Esterification. So there's Fischer to esterification, in which you take an alcohol and carboxylic acid. You can use tosylate esters, sulfate esters, nitrate esters, as well as phosphate esters. In terms of Fischer esterification, your alcohol essentially reacts with an acid to form the ester and water. Sulfuric acid is the catalyst, right? So what will happen is electrons from your oxygen will take that first, right? So then that would be protonated. I'm going to OH2, and then O. So then the rest of your acid, right? So this can leave, and this can react, forming the ester. The reaction is in an equilibrium between starting materials and products, and for this reason, Fischer esterification is seldom used to prepare esters. The other way to produce esters is to react alcohols with acid chlorides, shown here. With acid chlorides, you can generate esterification better, and the reaction is exothermic, producing corresponding ester in high yields with only HCl as the byproduct. And so you can have electrons go kick this off, and then Cl plucking off that hydrogen. So here, I'm just going to draw that. Right, electrons will come up, electrons will come off, kicking this once you have ROCOR, right, with your H already intact. You're going to have your Cl minus in the solution because you kick that off, taking that, plucking that hydrogen off, neutralizing the positive charge, and producing your nitrate esters. Best known nitrate ester is nitroglycerin, shown here. That name, the systematic name for that is glycerol trinitrate. In the presence of nitric acid will essentially form the glycerol trinitrate and 3 equivalents of water. So this is another way to form esters, nitrate esters in this case. You can generate phosphate esters by taking phosphoric acid and reacting with methanol, generate a monomethyl phosphate, another equivalent dimethyl phosphate, and another equivalent with a to form the trimethyl phosphate. And in these cases, your source of electrons are here, right? This will get kicked off. So you'll generate the methyl version of it. The methyl version would have a proton attached to it, and then the OH minus will come in, pluck off that proton, neutralizing that positive charge, and generating the monomethyl phosphate. So yeah, that was just showing you kind of how the mechanism is, and then you can do the rest for each equivalent. Phosphate esters, there are phosphate esters in DNA. Here's an example of DNA with a phosphodiester bond. And another way you can generate ethers are through Williamson ether synthesis using alkoxide now instead of using an alcohol. So here you have an alkoxide. So your nucleophile react SN2, kick it off. It's either a halide or tosylate, then you generate your ethers. So this is, important thing is that this is an SN2 displacement reaction. Therefore, it works best with primary halides. If secondary or tertiary halides are used, the alkoxide will act as a base, and then you'll have elimination. So this is the last slide and ends chapter 11.